What if everything you've ever known, every star, every galaxy, every atom that makes up your very being, emerged from a moment so cataclysmic, so incomprehensibly powerful, that its echoes still ripple through the cosmos today? Did you know that right now, as you watch this, scientists are using the most extraordinary machines ever conceived to peer not just across vast distances of space, but into the deepest chasms of time itself? They're not just looking at distant stars. They're gazing at the very first moments after existence flickered into being, uncovering secrets that have been hidden for billions of years. Prepare to embark on an unparalleled journey, a cosmic detective story where we seek to understand the very origins of everything, unraveling the mysteries of our cosmic birth. This isn't just science, it's the ultimate origin story, a revelation of how the universe became the breathtaking, mysterious expanse we inhabit. Imagine, if you can, a moment before time truly began, an infinitely hot, infinitely dense point, smaller than a single atom, yet containing the entire blueprint of reality. Then, in an instant that defies comprehension, an event of unimaginable scale occurred. The Big Bang. It wasn't an explosion in the traditional sense, but rather an incredibly rapid expansion of space itself, carrying with it all the energy and matter that would ever exist. For the briefest fraction of a second, the universe was a superheated, primordial soup of fundamental particles, a plasma so dense and energetic that light couldn't even escape its fiery embrace. This was the moment of creation, the genesis of everything we perceive, a flash of cosmic brilliance that set into motion the grand symphony of the universe. From this singular, astonishing event, the vastness of space and the relentless march of time began their epic journey, unfolding against a canvas of unfathomable power. In the immediate aftermath of the Big Bang, the universe was a chaotic, almost featureless expanse. It was a universe without stars, without galaxies, without any of the celestial structures we see today. For hundreds of millions of years, it was dominated by a hot, opaque plasma of hydrogen and helium nuclei, along with a sea of free electrons. But as the universe expanded, it cooled. Slowly, agonizingly, the temperature dropped to a critical point where electrons could finally combine with atomic nuclei, forming the first neutral atoms. It was at this crucial juncture, around 380,000 years after the Big Bang, that the universe finally became transparent to light. This was a monumental turning point, the cosmic dawn when light could finally stream freely through space, creating a residual glow that we can still detect today, a faint whisper of creation, a ghost of the universe's earliest breath. This period of cooling and transparency paved the way for the emergence of the first true illuminators of the cosmos, the first stars. These weren't like the stars we see today, rich in heavier elements forged in previous stellar generations. The very first stars, often called population 3 stars, were immense, monstrous entities, hundreds or even thousands of times the mass of our Sun, composed almost entirely of pristine hydrogen and helium. They lived fast and died young, burning with an almost unimaginable ferocity. Their formation marked a pivotal transition, as gravity slowly pulled together vast clouds of the primordial gas. When these immense gas clouds finally collapsed under their own weight, temperatures and pressures at their cores reached the critical thresholds for nuclear fusion to ignite, flooding the dark, nascent universe with their brilliant, searing light. These colossal cosmic illuminators were more than just points of light. They were cosmic factories. Within their scorching cores, hydrogen and helium were fused into the first heavier elements, carbon, oxygen, iron. When these titanic stars eventually met their explosive end as supernovae, they didn't just scatter these newly forged elements across space. They also sent powerful shock waves rippling through the interstellar medium, compressing surrounding gas clouds and triggering the birth of new generations of stars. This was the universe's first grand act of cosmic recycling, an essential process that slowly enriched the otherwise barren expanse. Without these first stars, the building blocks for planets, for life itself, would never have existed. They were the trailblazers, the pioneers that seeded the universe with the very ingredients necessary for complexity and for the eventual emergence of everything we know and hold dear. The period following the emergence of the first stars was a universe in profound transition. From a hot, featureless plasma, it began to sculpt itself into the intricate cosmic web we observe today. Gravity, the master sculptor, started to pull together not just individual stars, but vast assemblages of stars, gas, and dark matter into the nascent structures we recognize as galaxies. These early galaxies were likely smaller, more irregular, and far more active than their modern counterparts, undergoing intense bursts of star formation and frequent mergers. It was a violent, dynamic era, a time of cosmic construction where the fundamental forces of nature were actively shaping the universe's destiny. This evolution from an amorphous, uniform state to one filled with distinct, complex structures represents one of the most remarkable transformations in the history of the cosmos, a journey from simplicity to breathtaking complexity. Amidst the swirling chaos of the early universe as it gradually cooled and expanded, a profound artifact was left behind, a silent, ancient witness to creation itself. This isn't just a remnant, it's a cosmic fingerprint, a literal echo of the Big Bang. We call it the Cosmic Microwave Background, CMB, and it's perhaps the most important piece of evidence we have for the universe's fiery birth. Imagine the universe in its infancy as a colossal, glowing fireball, so hot and dense that it was opaque, like peering into the heart of a star. Then, approximately 380,000 years after the Big Bang, something transformative happened. The universe cooled enough for electrons and protons to finally combine and form neutral atoms of hydrogen and helium. This event, known as recombination, made the universe transparent for the first time, allowing photons, particles of light, to stream freely through space. These ancient photons, released from the universe's primordial glow, have been traveling across the vast expanse of the cosmos for nearly 13.8 billion years, stretched and cooled by the continuous expansion of space. Today we detect them as a faint, uniform glow of microwaves coming from every direction in the sky. This is the afterglow of creation, a perfect snapshot of the universe when it was just a baby, a mere blink of an eye in cosmic time. It's like listening to the last whisper of a colossal explosion that happened eons ago, a whisper that still carries vital information. The CMB isn't perfectly uniform. It has tiny, almost imperceptible temperature fluctuations, hotter and colder spots that are only millionths of a degree different. These minute variations, however, are profoundly significant. They are the seeds, the primordial density fluctuations, from which all the structures we see today, from individual stars to colossal galaxy clusters, eventually grew through the relentless pull of gravity. The cosmic microwave background isn't just a pretty picture. It's a treasure trove of data, revealing the universe's first moments with astonishing clarity. By meticulously analyzing the patterns and properties of the CMB, cosmologists have been able to pinpoint the age of the universe with incredible precision, currently estimated at 13.8 billion years. They've also determined its composition, confirming that ordinary matter, the stuff that makes up stars, planets, and us, accounts for only about 5% of the cosmos. The vast majority, a staggering 95%, remains shrouded in mystery, composed of enigmatic dark matter and dark energy, which we'll delve into shortly. Furthermore, the CMB provides crucial insights into the expansion rate of the early universe, corroborating the Big Bang theory and offering clues about the forces that shaped its initial evolution. It's like having a perfect baby picture of the universe, and from that single image we can deduce its entire life story up to now. One of the most mind-bending theories suggested by the uniformity and flatness of the CMB is cosmic inflation. Imagine the universe not just expanding after the Big Bang, but undergoing an unimaginably rapid exponential growth spurt in the first fleeting fraction of a second, far faster than the speed of light. This isn't a violation of Einstein's theory of relativity, because it's space itself that's expanding, not objects moving through space. This theory posits that the universe inflated by a factor of at least $10(26), that's a 1 followed by 26 zeros, in an absurdly short time, perhaps less than $10(-32) seconds. Such a rapid expansion would have smoothed out any initial irregularities, explaining the remarkable uniformity of the CMB and solving several perplexing puzzles about the early cosmos. It's a breathtaking concept, transforming a tiny quantum fluctuation into the vast, observable universe we see today, setting the stage for everything that followed. Cosmic inflation isn't just a theoretical elegance. It provides a compelling framework for understanding how such a massive, yet surprisingly uniform, universe could have emerged from the chaos of the Big Bang. It explains why the universe appears flat, on cosmic scales, much like how the Earth appears flat from our perspective, even though it's a sphere. This flatness is crucial for the universe to evolve in a way that allows for the formation of galaxies and, ultimately, life. Furthermore, inflation predicts the precise patterns of the tiny temperature fluctuations we observe in the CMB, acting as the quantum seeds for the large-scale structure of the universe. It implies that these minute ripples, stretched to cosmic proportions by the inflationary epoch, are the direct progenitors of the superclusters of galaxies, the vast cosmic web that threads through the universe, a silent testament to a primordial force beyond our immediate comprehension. While the CMB gives us a perfect baby picture, it doesn't show us the universe's awkward teenage years, the epoch when the first stars and galaxies truly burst into existence. This is where cosmic archaeology comes into play, a relentless hunt for the universe's earliest building blocks, pushing the boundaries of what telescopes can achieve. For decades, peering beyond the CMB into this dark ages of the universe seemed almost impossible. But now humanity possesses a new set of eyes, capable of piercing through the cosmic veil, allowing us to witness the dawn of galactic formation. This is the realm where the biggest and most ambitious space observatories earn their stripes, pushing back the frontiers of our knowledge with every photon they capture. It's an astronomical endeavor that demands immense precision and cutting-edge technology, revealing glimpses of a time when the universe was barely a toddler. The most revolutionary tool in this cosmic archaeological dig is undoubtedly the James Webb Space Telescope, JWST. Launched to an orbit millions of miles from Earth, equipped with a massive golden mirror optimized to detect infrared light, JWST is revolutionizing our understanding of the early universe. Unlike its predecessor, Hubble, which primarily sees invisible light, Webb's infrared capabilities allow it to detect the incredibly faint, redshifted light from the most distant and therefore oldest galaxies. As the universe expands, the light from these distant objects gets stretched, shifting from visible wavelengths into the infrared spectrum. Without JWST's unparalleled sensitivity to infrared, this ancient light would remain undetectable, leaving the earliest chapters of cosmic history unread. Its observations are not just confirming theories, they are challenging existing models, pushing scientists to re-evaluate our understanding of how quickly galaxies formed after the Big Bang. Through JWST's incredible observations, we are now getting our first clear glimpse of the first galaxies, which formed just a few hundred million years after the Big Bang, mere blinks in cosmic time. These weren't the grand spiral or elliptical galaxies we see today. They were likely smaller, more chaotic and intensely active, undergoing furious bursts of star formation. These cosmic building blocks were vital for the universe's chemical evolution. Within their early, massive stars, the first heavy elements were forged through nuclear fusion. When these stars died in colossal supernova explosions, they scattered these essential elements, carbon, oxygen, iron and countless others, into the surrounding interstellar medium. These elements, in turn, became the raw material for subsequent generations of stars, planets, and ultimately life itself. Without these pioneering galaxies, the universe would remain a sterile, hydrogen-helium-rich void, devoid of the complexity that makes our existence possible. The discoveries made by JWST are painting a picture of an early universe that is far more vibrant and rapidly evolving than previously imagined. We're seeing evidence of galaxies forming much earlier than theoretical models predicted, and some appear to be surprisingly massive and mature. This challenges our understanding of how quickly structures could have assembled in the early, less dense cosmos. It suggests that the forces driving galaxy formation, gravity, dark matter, and even unknown processes, were incredibly efficient during this epoch. This rapid emergence of galaxies also contributed to a crucial period known as the epoch of reionization, when the light from these first stars and galaxies stripped electrons from the neutral hydrogen atoms that had filled the universe since recombination, effectively reionizing the cosmos and making it transparent to light once again. This reionization was essential for light to travel freely to us today, making the universe truly luminous. However, despite these groundbreaking discoveries, a vast portion of the cosmos remains stubbornly out of reach, constituting what we call the dark universe. This isn't just about what we can't see, it's about what we believe exists based on its gravitational effects. We're talking about dark matter and dark energy, two of the most profound mysteries in all of science, together making up an astounding 95% of the universe's total mass and energy. Dark matter, an invisible substance that doesn't interact with light, acts as the gravitational scaffolding for galaxies and galaxy clusters. Without its unseen pull, galaxies simply wouldn't hold together or form in the way we observe. It dictates the large-scale structure of the universe, guiding the formation of cosmic filaments and voids, yet its true nature remains elusive, a ghost in the cosmic machine. Then there's dark energy, an even more perplexing enigma. This mysterious force is believed to be responsible for the accelerating expansion of the universe. For billions of years, gravity was expected to slow down the cosmic expansion, but observations have revealed the opposite. The expansion is speeding up, as if some unseen energy is pushing everything apart. Dark energy dominates the universe's energy budget, controlling its ultimate fate, yet we have no idea what it is or where it comes from. These two dark, components play extraordinarily significant roles in the evolution of the universe, influencing everything from the distribution of galaxies to the ultimate destiny of spacetime itself. Understanding them is not just a scientific curiosity, it's fundamental to completing our cosmic origin story, and the hunt for their true nature is one of the most exciting and challenging quests in modern cosmology. The quest to unlock the universe's most profound secrets is not a finite race with a clear finish line. It is an eternal journey, fueled by humanity's insatiable curiosity and an ever-evolving toolkit of unprecedented technology. The future of cosmic exploration promises to plunge us even deeper into the cosmos, to eras and phenomena once thought utterly beyond our grasp. Upcoming space missions are not mere incremental steps. They represent colossal leaps, designed to challenge our most fundamental assumptions about reality itself. Imagine not just peering further but feeling the universe in new ways. The upcoming LISA, Laser Interferometer Space Antenna, mission, a colossal space-based gravitational wave observatory, will listen for the echoes of merging supermassive black holes and the faint, primordial gravitational waves left over from the Big Bang itself. These are ripples in spacetime so ancient, so subtle, that they hold the key to understanding events that unfolded even before the cosmic microwave background formed, offering a direct window into the very first slivers of a second after creation. Beyond gravitational waves, the next generation of ground-based observatories, like the European Extremely Large Telescope (ELT) and the Giant Magellan Telescope (GMT), will boast mirrors tens of meters in diameter, collecting light with unparalleled sensitivity. These behemoths will allow us to scrutinize the atmospheres of distant exoplanets, search for the faintest glimmers of the very first stars born in the universe, and even directly observe the formation of galaxies in real time. We are building machines that are, in essence, time machines, allowing us to rewind the cosmic clock to epochs where the universe was still finding its form. These aren't just scientific instruments. They are monuments to human ambition, tools that promise to fundamentally rewrite our cosmic textbooks and force us to confront realities far stranger and more magnificent than any we currently comprehend. The quest for cosmic origins is accelerating, revealing secrets previously whispered only in theory. But the future of cosmic exploration isn't solely a look into the past, it's a desperate, hopeful gaze towards the future. Specifically, the hunt for exoplanets and the search for life beyond Earth. Imagine staring into the void, knowing that somewhere out there, on a world orbiting a distant star, conditions might be ripe for life. Missions like the proposed Habitable Worlds Observatory, a space telescope far grander than even JWST, aim to not just find, but characterize Earth-like planets, scrutinizing their atmospheres for chemical signatures that scream life. Oxygen, methane, water vapor. These are the potential whispers we seek, carried across light years, telling us if the intricate dance of chemistry and biology that birthed us has occurred elsewhere. The implications are staggering. If we find evidence of life, even microbial, it would shatter our perceived uniqueness, transforming humanity's place from a solitary miracle to one thread in a vast, living cosmic tapestry. This isn't just about spotting a distant speck, it's about discerning the very breath of an alien world. The development of advanced coronagraphs, instruments that block out the blinding light of a parent star to reveal the faint glow of its planets, is critical. Future missions might even deploy arrays of space telescopes working together as a giant interferometric eye, providing enough resolution to resolve surface features or even continents on exoplanets. And beyond detection, the ultimate dream remains interstellar travel, even if in rudimentary forms. Concepts for tiny laser-propelled nanocraft, capable of reaching nearby star systems in decades rather than millennia, are no longer purely science fiction. While monumental challenges remain, the sheer thought of physically touching down on another living world, confirming humanity is not alone, propels this hunt for life beyond Earth with an urgency that borders on spiritual. Ultimately, every new discovery, every advanced instrument, pushes us beyond our horizon, forcing us to confront the universe's grand design. It's a design that speaks of elegant simplicity giving rise to breathtaking complexity. From the initial quantum fluctuations that seeded the vast structures we see today, to the relentless pull of dark matter sculpting galaxies, and the mysterious push of dark energy accelerating the universe's expansion, there's an underlying logic, a cosmic choreography at play. We are witnessing the unfolding of cosmic evolution on an unimaginable scale, a journey that began with pure energy and is steadily progressing towards ever greater order, structure, and perhaps consciousness. The universe is not just a collection of random events. It is a symphony, its movements guided by fundamental laws, leading to formations of awe-inspiring beauty and complexity, making our very existence a profound consequence of its vast, intelligent design. The significance of cosmic exploration transcends scientific accolades or technological prowess. It delves into the deepest philosophical questions of our existence. To truly grasp the origin and evolution of the universe is to understand our cosmic ancestry, our fundamental connection to the stars. Every atom in your body, from the carbon in your bones to the iron in your blood, was forged in the heart of a dying star billions of years ago. We are literally stardust, sentient dust capable of looking back at the very processes that created us. This profound realization shifts our perspective, reminding us of our fleeting yet precious place within this vast, dynamic cosmos. It inspires humility, wonder, and a sense of interconnectedness that few other fields of human endeavor can provide, grounding us in a narrative far grander than any single human story. The future directions in cosmology are painted with the promise of unprecedented revelations. Imagine cracking the code of dark matter, finally understanding what constitutes the universe's invisible scaffolding. Or perhaps detecting definitive proof of dark energy's nature, unraveling the ultimate fate of the cosmos. Will it expand forever into a cold, dark oblivion, or will it eventually collapse in a reverse Big Bang? These are not mere academic questions. They are the ultimate riddles that define our cosmic destiny. The coming decades will see us construct telescopes larger than any ever conceived, deploy probes to distant ocean-filled moons, and perhaps, for the first time, receive a definitive answer to whether we are truly alone. The universe is speaking, and we are finally developing the ears to listen, the eyes to see, and the minds to comprehend its ancient, powerful voice. This relentless pursuit of knowledge, this drive to uncover the secrets of the early universe, is the highest expression of humanity's intellectual curiosity. It is a testament to our innate desire to transcend the known, to push past the comfortable boundaries of our planet and gaze into the infinite. It is a journey that demands courage, perseverance, and an unwavering belief in the power of inquiry. The universe rewards those who seek its truths, constantly revealing new layers of complexity, new wonders that humble and inspire us in equal measure. This is a story that continues to unfold, its most thrilling chapters still unwritten. So, as you step away from this cosmic narrative, carry with you the awe, the wonder, and the burning questions that define our shared human experience. Don't let the vastness intimidate you, let it invigorate your spirit. Continue to learn, to question, to explore, even if only from the comfort of your home, through books, documentaries, and scientific updates. Share this wonder with others, spark their curiosity, and encourage the next generation of explorers, scientists, and dreamers. Because the universe is not just for the experts, it is for all of us. This is our cosmic heritage. It is beckoning. Are you ready to answer its call? The greatest discoveries are still out there, waiting for minds like yours to find them. ***.